A very good morning to one and all present here. Approximately, we are having 70 participants now. Expecting others also will join soon. Once again, a very good morning to one and all present here. I, Renu J. requesting all the participants to kindly mute your mics. Participants are requested to mute your mics. We are starting the session for today. Yeah, thank you. Hey, very good morning to one and all present here. Hi, Renu J. Vijayan, on behalf of College of Engineering, Talasheri, welcome all of you to the second day of our ATAL-sponsored 5-day FDP on electric vehicles, challenges in charging and their impact on power grid phase 1, organized by Department of Electrical and Electronics Engineering. Today we have Mr. Sajin Ismail, Assistant Engineer in Kerala State Electricity Board, as our first spokesman. He is connected with the Innovation Division, Office of the Chief Engineer, Renewable Energy and Energy Savings, KSEBL Limited. It's a great pleasure for me to introduce our speaker today, who is going to talk to us about the EV charging technology and its grid interaction. This is in fact a subject in which we should all be deeply interested. Now I wish to give you a quick glance at Sajin's profile. Sajin had completed his BTech from Marbasilius College of Engineering, Trivandrum, and his MTech from Vellore Institute of Technology. Our speaker, although have started his career as project engineer in Power Electronics Division in Keltron, and subsequently as project engineer in CDAC, his dedication and hard work propelled him to become the assistant engineer in KSEBL Limited in the year 2018. During his probation, he has proved his excellence by becoming the gold medal winner for the best probational assistant engineer trainee. It is indeed our great pleasure to have you as a part of this FDP, sir. I extend our warm welcome to Sajin Ismail for a magnificent technical session. Over to Sajin Ismail.
Thank you, Renu. Can I share the PPT now? You can hear me now?
Yes. You are perfectly audible and you can share your PPT.
Okay. PPT visible now to everyone? PPT?
Yeah. It's visible.
Okay. Once again, thank you, Renu, for your wonderful introduction. And it was flattering indeed. So before not giving any much time to anything else, I'll just straightly go ahead to the topic. So since it's a topic of relevance, what I would like to give you is I'm working in a utility, and the introduction of electric vehicles across the continent or the world itself is creating a lot of issues, and it is a need of the hour also. So in today's discussion, what I would like to tell you is we'll be discussing on what is the possibility of grid integration of an electric vehicle. How do you integrate it? So when you integrate an electric vehicle, so what will be the issues and challenges associated with that? And the second part of the topic presentation will be what are the opportunities that is given by the electric vehicles when you connect them to the grid. It will create issues, and at the same time it can create some opportunities also. Then some of the advanced technologies that is being considered to be growing in the future, and it will really control the power sector market in the future, that is considered as V2X system, and the renewable integration with electric vehicle charging, and finally the concept of smart charging. These will be our topics of discussion today. Let me go to the first slide. So the grid integration of electric vehicles and its impacts. As we know, electric vehicles are in our market right now. It was there earlier, but the growth is actually increasing due to many factors: the global warming effects, the price of conventional fuels, and the pollution it creates, greenhouse gas emission reduction. A lot of things are there that is actually fueling to the rise of electric vehicle adoption in our country. But it is actually going in a fast pace. No, it has a lot of issues. One of the things that is affecting is the lack of infrastructure, like electric vehicle charging infrastructure, the development of it, the issues relating to that. I have a session in the afternoon. We'll discuss detail about the development of electric vehicle charging infrastructure in Kerala and the glimpses of growth in India as well. But today we'll be strictly discussing about when we connect the electric vehicle to the grid, the issues. So as the number of electric vehicles are less right now, we are not facing much issues in the grid. But as the number of vehicles will be increasing, as we know, in if even though if the number of vehicles and the demand of electric vehicles are less right now, it is going to be there. Tomorrow, if not today, tomorrow the electric vehicles will rule the transport sector. Everything will be converted to electric, at least to 80 to 90 percentage for sure. If some alternate fuels like hydrogen will kick in, it may hold some share, but electric vehicles will be the future. But at that time, will our nation or our states will be ready to provide that much of power that need to power these vehicles? So we can check on the statistics. In 2000, India is considered as an energy surplus nation, or but some states are not at all. In Kerala, we are not at all an energy surplus state. We are an energy deficient state. We are getting power across from many states from the country. But again, India is considered as a power surplus, so we can give power to required states and all the locations. But in 2018-19, there was a peak power deficit of 0.8 percentage. It was reported that. We'll explain how it is going to affect the EV charging infrastructure and its grid integration later. Again, the another important aspect we should know is that e-mobility is a concept that is not simply related to transport sector or power sector. It has a deep confluence between both the transport and power sector. So when we integrate it with the grid, there will be, as I said earlier, there will be a lot of challenges. At the same time, opportunities will also create for the power sector. As a person for power sector, we are facing two parts. We are facing a lot of challenges, or we are really anxious how it is going to be. But at the same time, it is showing some light that it will provide some opportunities to the operator as well for revenue making as well. Now, when we connect an electric vehicle to the grid, not one or two vehicles, when it will increase the number of vehicles to a substantial level, what are the challenges that we are actually going to face in a technical perspective? I'll go one by one, and there will be issues that actually I hope that you are all from either a postgraduate researchers or doctorate, postdoctoral fellows or doctoral fellows or research students. So you can take up many of these subjects and actually give light to the utilities on how you should approach this issue in the future. So I'll start with the first issue, that is voltage stability issues. As we know, the distribution lines here, we can see our distribution lines. The R by X ratio is normally high in distribution lines. The reactance value is lesser. So definitely R by X ratio will be high. So it will itself, generally due to this high ratio, these distribution lines are more susceptible to voltage sags because of the high power drawn. So whenever there is a high power demand, these distribution lines will show the they are susceptible to voltage sags. So what happens is when the voltage is sagging, that means voltage is reducing from its rated value. So there is stable operating voltage is being changing. So that means it can lead to an unstable voltage operating zones, or it is being moving from stable operating zones. So this is a general perspective. So how it is going to affect the EV charging? So say example, we can see we can consider a home in which we have a connected load of a normal middle class family will have 3 to 5 kW maximum. Most of them are working in single phase connection also. Only a few people will have like 7 kW or more than that. At that time, when you are connecting an EV charger, a minimum EV charger of a small vehicle will be like a four-wheeler I'm talking about, it will be 3.3 kW. So our total connected load at home will be 2 kW or 3 kW. The same power is required for an electric vehicle. Sorry. Can I continue?
Yes, yes, yes. You can continue.
Yes.
Okay.
Yes, sir.
Okay. Thank you. Okay. What I was talking is whenever there is this electric vehicle, we are charging at home. The total connected load at home will be 3 kW. At the same time, a minimum charger will the load will be 3.3 kW. So we can understand compared to the other residential loads, the load requirement of an electric vehicle charging infrastructure will be very high, even at a home level. So what will happen is the power demand will be very high when we are charging an electric vehicle. So this is happening at one home at a lower rated vehicle. When it is happening at numerous number of homes and numerous number of public charging stations where the power capacity will be varying from 50 to 200 kW or above for higher capacity vehicles, what will happen? The higher EV penetration will create this issue of power demand in a grid which is already low. Already the distribution lines are facing this low voltage situation due to the uh, condition I already explained earlier. So what happens? This much of EV penetration and this much of loading, power demand will totally create voltage stability issues. And it's for sure that voltage stability issues will come. And how is it going to aggregate it? Normally, we understand that we'll classify one particular time of the day as the peak period in power sector. Why? Because at the time everyone will be using power, probably 6 to 10 that period. Everyone will be turning on their lights, TVs, everything. So that is why it is called peak power. Every utility is facing a huge issue to meet the peak power demand. Whenever there is power deficiency, we'll have to find power from somewhere, or we'll have to go for even load shedding to maintain the power supply or balance the grid. At that time, an additional load of enormous nature is coming in. The grid will do what? It can simply sit and watch if it is not prepared for it. So that is what is going to happen when the EV charging period is going to coincide with the peak demand period. You can see I'm showing it as a small yellow part. This is just a small joining. When it is becoming, the area of this part is increasing, what happens is the aggravation of voltage stability will be very high, because already the peak demand is very difficult to harness. In Kerala itself, we are really facing trouble in bringing power from other states and all, and maintaining the load dispatch center is controlling it. So what happens is the enormous requirement of electric vehicle charges, charging power is required, and at the peak time, what happens is the situation will be very, very bad. So this issue can come. Not every owner of an electric vehicle won't understand what's the difference between peak power and normal power. He can, if I want to run my vehicle, I have to charge. I'll charge it at peak or whatever time I want, because I am supposed to use it for transportational purpose, not for the control of the grid. This is exclusively for a person's use. So he will do it accordingly. So this is going to be a major issue that we need to be taken care of. So from a grid operator's perspective, he has to be very careful about this. Otherwise, the grid will have huge issues. Even it can turn out to blackouts as well. So here I'll show you a curve. Actually, this curve is showing the power to PV curve. This one is actually, when you see, based on the line resistance and reactance, each bus has a critical voltage. You can see this, and which corresponds to the maximum active power that can be drawn from the bus. And any further increase in the load at this bus will lead to voltage collapse. So there is a limitation of power. A critical voltage will be there for every voltage bus. So at the time when you are increasing the power demand, after a substantial level, when it is crossing that, the voltage will droop and there will be an unstable operation of voltage. This is the curve based on the power demand. So this is what we are going to face in the future. And one more thing, the ratio of change in voltage due to change in active power is termed as voltage sensitivity factor. So we can see what happens is the active power demand is what has been required from the electric vehicle chargers. So this because the vehicle is demanding power, so the electric vehicle charger will demand it from the grid. So there will be a huge demand for power, active power, and it will create a change in voltage. And what happens is with this condition, the high voltage sensitivity factor will come in, and for small changes in active power there will be a large drop in voltage, and which will create huge issues. When there is voltage dip, many equipments will not work, even the charger itself cannot work, the other chargers, other locations may even go in difficulty. Okay, this is the first issue which we talked about, the voltage stability. Now we'll go to the second part. This is about phase imbalance. So how can I talk about phase imbalance? Is we can understand that. She said most of our households are working in single phase because up to 5 kW we are not supposed to go for three phase. If you wish, you can go for, as per Kerala State Electricity Supply Code, it is clearly mentioned that up to 5 kW only single phase connection is required at a home or any place. So what happens is, in India, we have a peculiar market. The demand for three wheelers and two wheelers is considerably high comparing to other nations. The electric autos, electric two wheelers are in more number. When we are converting the number of present electric vehicles to present conventional IC engine vehicles to electric vehicle in the future, the more number will of course be two wheelers.
Hello, Sajin. Some problem is with your mic. You are not audible for us. Yes, your mic is muted. Sajin.
Can you hear me now?
Yeah, now it's audible, Sajin.
Okay.
Yeah.
From where you heard last part? Did everyone hear about the phase imbalance, or should I start from it again?
No. It's better you start from the phase imbalance because thereafter some audible issues was there.
Okay. I'll start again from the phase
Yeah.
imbalance.
Okay. Thank you, Sajin.
So the phase imbalance again. The issue with phase imbalance start from our taste for electric vehicles. I mean, basically vehicles in India. Two wheelers and three wheelers are the major shareholders in the transport sector. So what happens is, in the future also the electric two wheelers and three wheelers will emerge in India first. Then only the four wheelers will become a significant force. So what happens is, due to this massive two-wheeler and three-wheeler entry, and they will not be depending upon the public charging stations also, they'll be charging from homes. And these two-wheelers and three-wheelers have a charger which will be 3.3 kW, and they'll be charging from their home. These are single phase chargers predominantly. So what happens is, when you are using a single phase charger in a system, in a distribution system, we have three phases from a distribution transformer. And if most of the charges are being distributed among one particular phase, or if it is not being distributed evenly, what happens is, at one particular phase the demand will be very high, 3.3 kW into 10, 10 houses will become 33 kW demand will be there. In other places, it will not be there in other phases. So it will create a huge unbalance. If we cannot, the grid operator cannot imagine that wherever the chargers are coming, at present we can just think that only few vehicles are coming. But when in the future too many will come, the capacity ratings will be different. So what happens is it will create a huge problem. So, as we know, unbalanced operation of the network results in higher losses in the network, voltage issues, and which is detrimental to overall system health. As we know, one phase is higher than the other two phases. As I said earlier, in three phases, one phase, the power demand is very high. The voltage drop at that particular phase will be high. But in the other two phases, the demand is less. So what happens is there will be over voltage in other two phases. So what happens, we know as from the power system understanding, we know that when there is this much of unbalance is there, there will be neutral point shifting. So over voltage in one particular phase or two phases and under voltage in one phase will create enormous issues, which can even affect the other households equipments which are supposed to work at a lower voltage. The higher voltage will go there, the equipment will get damaged, and issues like that will come. So shifting of neutral point may occur if you are not properly distribute the charges among the phases of a distribution transformer in a distribution network. So this is a very important issue that need to be taken care when the number of electric vehicles are getting higher in the market. The distribution of the chargers should be careful, because as I said, 3.3 kW minimum of single phase charger will rate. Now, the next point is the increase in peak load. As I said earlier, this is a major issue that we are going to face in electric vehicle throughout the discussion of our topic. This is the crux. The charging nature of EV can be controlled, but if it is uncontrolled, it could increase the peak load. If the charging is being done without any rational, any thinking, if you charge, everyone is charging at a peak demand time and the power requirement is already high for other things, when we are increasing this demand for electric vehicle charging, it will coincide with the load peak and it will totally devastate the grid. So this would contribute to overloading, of course, of the transmission and network, and of course it will affect the assets like transformers and cables. So the line will be overheated, the transformers will be overloaded. After a period of time, what happens is that the equipments will be damaged, equipment's life will be affected, the lines will be broken, the issues will be very high, and this extra load will also lead to the increase in generation and the increase in the electricity price. What happens is, at present, what we'll try to buy at peak power also from power exchanges, a power that is considerably lower price. That is what we'll try. We will try to share the peak power, but what happens is when the requirement is very high, the utility will be forced to buy power from those places which is, or those thermal power plants or other conventional plants where, or any plant which is providing for a higher rate at that time. So this will substantially increase the electricity price as well, because the power has to be given, the power is not available, we'll have to take from anywhere, whoever is ready to give the power. The next part is, as I said, the peak power is increasing, the load is increasing. That means definitely overloading. The coincidence of EV charging with a network peak load may further stress the system. As I said earlier, this increased EV load, it can cause overloading in different assets. As I said, the distribution network will be totally affected. The distribution transformers, cables, fuses. So the reliability index will come down. We'll talk about the reliability factor later. But again, the equipments are being suffering because of this overload. They are not ready. If the grid has been ready to accept this power.
Hello.
Hello. Hello.
Sony ma'am, please mute your mic. Sony ma'am. Yes, Sajin, you can continue.
Okay. So this overloading in a significant for a continuous period, it will totally affect the system, and it will in turn the system, the equipments are being getting damaged. That means the efficiency of the system is there. There will be power outages, issues like that. The grid should be ready to take over the kind of requirement that will come. Now the power losses, as we can say, the demand will be high means the current will be high. Current will be high means I square R losses will be high. So the power losses will be there. So with this added current flow through these lines due to the extra EV charging load, the loss in the system also increases, making the supply of power less efficient. As I said earlier, so this current is unwanted, this unwanted demand is coming, so the network is not ready for it, so the losses will be high. Again, and unbalanced loading can lead to uneven losses among the three phases that we have discussed earlier. Now, coming to another major aspect, a major challenge that everybody might be knowing from the research perspective, that is power quality. As we know, we already face this situation not just from electric vehicles. The power quality issues are majorly created by the power electronic devices. They are AC to DC converters. The issue, I'm audible now. My mic is getting automatically
Yes,
muted.
you are audible now, but when you started the power quality, at some portion it got
Okay.
muted. When you were
Okay.
explaining that power quality description, it got muted for a while.
Okay. I'll start again.
Yeah.
From power quality. So the power quality issue that everybody will be knowing, that the power electronic loads are always the reason for power quality issues, because the power electronic converters, AC to DC converters or DC to DC converter, these are creating harmonics, and they are really affecting because they are nonlinear loads. It's not just the electric vehicle charges. We are having inverters and many SMPS. A lot of nonlinear loads are there already in the in the system. So it is itself creating a lot of harmonics. But the adoption of electric vehicles will create the demand of chargers. That means the number of chargers will be huge, and the introduction of power electronic converters, these non-linear loads, will be huge, and it can give a significant increase in the harmonic distortion in the voltage supply, and this is going to be a huge problem in the future as well. So the level of distortion, as it is mentioned in my presentation, the level of distortion is proportional to the number of EV chargers operating simultaneously in a distribution network. So when you have one or two chargers, we feel that okay, it's a couple of chargers, it's a big grid, it's not going to affect that much. When the number of EV chargers are increasing, the level of distortion will not be in our hand, it will go really high. So the EV chargers also bring voltage excursions, which the end use customers can detect as flickers in the lighting devices or change in speed in the electrical motors. So another problem it can create is, as I said again, I said earlier, the voltage imbalance will be there due to the harmonics. There will be voltage, the waveform will be totally distorted. So these distortions and imbalances can create voltage excursions. It will vary from one point to another point, and which can even create flickers in the fluorescent lights and incandescent lamps. And at the same time, the electrical motors like your fans and other equipments, the speed will also vary because of the voltage is changing. So as we know that, I hope that you all will be uh, well aware of the harmonic content and the calculation of it, how we calculate a harmonic content, a particular harmonic frequency and all. I'm not describing much about it. The conductor loss due to this harmonic current. This is a distortion factor is coming in the current, and distortion factor is creating an additional current, and that will definitely become a loss. It will be an additional loss that is creating to the existing loss. So you can see the increased current leads to increase in conductor losses. You can see as the harmonic percentage, total harmonic distortion is increasing, the loss will increase. It's a natural thing to happen. But the why I'm again stressing it is this will happen. The increase in harmonic loads, like nonlinear loads are increasing. The loss of harmonics will be that created by harmonics will be high, and it need to be taken care of well. Next is about the neutral conductor. This is where our distribution transformers are facing the issue here. As we know that harmonics can be categorized into positive sequence harmonics, negative and zero sequence harmonics. And the third, sixth, and the ninth harmonics, the triplet harmonics, they are also called as zero sequence harmonics. Why? Because they are in phase with the fundamental frequency, so they will circulate among with them. So what happens is, as we can see in this graph, you can see this is the fundamental, the black one is the fundamental curve of the phase 1. This is R phase, Y phase, and B phase. We can see the third harmonic, which is in phase with the fundamental, we can see. And what happens is the blue one is the third harmonic, the triplet harmonic, which is shown here. With this, what happens is, with the generation of more triplet harmonics, we can see all the three phases. When you add them together, the neutral current will be I1 plus I2 plus I3. As we know, it should normally be 0, but what happens is it will add up. With if this harmonic content is not taken care of, it will add up, and what happens is this will be add up together, and this will be the neutral current. The additional current will form. This neutral current will be causing a lot of issues. This will be huge current creating due to the triplet harmonics if we are not addressing the harmonics. So, as I would like to suggest is the impact of harmonics in the distribution network due to the introduction of electric vehicle chargers can be a case study to be conducted, and anyone interested can conduct a case study in any household area where 10 or 15 chargers are there in one particular phase. You can study about it and understand how it is actually affecting the grid, and the effect of all these matters we have mentioned earlier. And similarly, it will affect other equipment such as motors and generators. The generators and motors are also affected by the harmonics in terms of efficiency reduction, overheating. As we know that harmonics is the major cause of overheating and derating. So the harmonics will give rise to decurrent and hysteresis losses. So it will simply, we can say the core loss will be increasing. Similarly, the current is getting high. So I squared R loss is increasing. Core loss and copper loss are increasing. So harmonic content is increasing means overall losses are really high. And the negative sequence harmonics have also affect the force against torque rotation, causing the motor vibration, added heat generation, and need for derating. So this is the effect of generators and transformers, and harmonics will create, whoever is the cause of it, whether the electric vehicle charging infrastructure, that means chargers or inverters or whatever it is, it will create issues to all the equipments associated with the grid or with the system. So reduction of harmonics is a very important aspect for any grid operator. So the loads are changing to nonlinear, and with the impact of electric vehicles, the change will be very high. It will be rapid, and it will be, the volume of it will also be substantially high. Now we can come to the transformers. So transformers are the potentially high risk component in a grid where the distribution transformers directly dealing with the EV chargers. So what happens is, if this harmonics is not taken care of at the charger level itself, and if it is injecting to the grid, it will definitely hamper it, because we know the distribution transformer primary is delta and secondary is the star connected. So the primary may not be affecting these harmonics because of the delta connection, but the secondary windings may affect. So there is also a potential risk of resonance between transformer inductance and the supplied capacity loads. This is only a potential risk is being suggested, but it at harmonic frequencies, if the harmonic frequencies are predominant only at that time. As we know, the noise and heat generation will also be there due to harmonics. I'm not stressing much on harmonics. And the circuit breakers will also face this issue. Again, These are all issues because of the generation of harmonics. Not stressing each and every one of them. We might be knowing the power quality issues are majorly created by the harmonic components that is been created. These components can affect every equipment. So how it is affecting that, you might be knowing better than me. So the thing about electric vehicle charging infrastructure to the grid is, how a researcher should approach to it is, the EV charging infrastructure, how it is creating the harmonics into the grid, how it can be mitigated, how it should be at the minimum level. Now, flickers, I have mentioned it earlier. Harmonics can create flickers. These are the fluctuations of light intensity. It's visible to human eyes. And uh, coming to the important part, as a grid representative, the impact of reliability. So, from the point of view of a power system, the EV charging changes the load pattern. That is the problem. The existing load pattern will totally change. Whenever an EV owner feel like charging, he can charge it. So there is no particular time. He can charge it anytime. The load pattern will significantly increase and it will totally change. Our load curve will not be the same again. And consequently, the generation needs. So that is a problem. So when the power is being generated at a time, that is being consumed also at the time, because the battery storage systems are not there. We are generating at the same time we are using. So the power demand is there. It has to be generated at that time itself. So the security of the supply is being hugely affected, because whenever the demand is suddenly coming from nowhere, because so many vehicles are getting charged at that point, so the impact is actually on the reliability of the power supply. The additional demand is highly stochastic and is dependent on the myriad of different factors, such as EV user travel behavior, charging time preferences, charging power required, time of charging. As I have explained it earlier, these are the factors of charging. So it is all in their mind, the user's mind, that we cannot control. And a case example is being given, because an AC charger, slow charger at home will be less than kW. If he feels like getting, it will take 7 to 10 hours for full charging. He feels like I want to get it charged immediately. So he's taking into the fast charger, 50 kW or 60 kW. So how much power demand is being changing? He is not charging from a 7 kW or 3.3 kW charger. He is immediately charging from a 50 kW. The demand will change. The power transfer within 1 hour will be like 30 to 40 kW. So it was supposed to be 3 kW. The demand of power will be changing at any time. This variability of power needs, this actually stresses the requirement of energy generation. So whenever is the demand is coming, the grid has to find power from somewhere. Further, if the distribution network is not designed to handle the added load, so what happens is, when we are setting up a public charging station, we'll ask them to set up a separate transformer if it is required. We'll discuss about the setting up in the afternoon session. But when it is at home, we might not even know they are having a charging point there. The distribution utility might not even know. So the failure rate of the distribution network asset may increase, substantially increase. The transformer is heavily overloading. The utility may not understand from where it is getting loaded. Suddenly it is increasing from a day onwards. After the transformer failure, we may know. So this is going to be a huge impact on reliability. In a distribution network, the reliability of the supply is closely related to the satisfaction of the end use customer. So if the customer can't charge it properly, the customer will feel that the system is bad. It is the system that is causing the issue. Of course, the system is causing the issue because the system is not prepared to take care of this load. So the system has to be ready. The system cannot be ready if it does not understand how this change is happening. So it's a coordinated effort between the chargers and the system should be there, and that we'll discuss in a later stage, and at how the solution of it. So these are the impacts. I hope the impacts of the EV charging infrastructure for charging electric vehicles to the grid that we have discussed. And again, another case study can be done and conducted, and the results will be very interesting to us also. That means the impact of reliability of power supply due to the increase in number of EV charging stations. You can conduct a study in an area where how it is the reliability of power is affecting after the number of charges is increased at that area. I would say preferably the residential charging stations, because the public charging stations might have the adequate power supply requirement, because with that only we are giving the supply to that. Now we have discussed about the impacts and challenges associated with the grid integration of electric vehicle. Now we'll go to another set of thoughts, that is, what are the support services that the electric vehicles can give. As I said earlier, the electric vehicles will create issues, but at the same time, the electric vehicle charging infrastructure, the EV charger, can provide something else also, some services to the grid. So what are they? As I said earlier, the primary application of an EV charger is to charge up the electric vehicle to satisfy the EV users' transportational needs. It's of course the transportational needs, but EVs can potentially perform a range of grid support activities. But how? We know that this is a power electronic controller. It will be there. It is charging the electric vehicle. So the point here is allowing bidirectional flow of power. The electric vehicle can be charged from the electric vehicle charger. At the same time, the excess power in the electric vehicle can also be transferred to the grid. The bidirectional transfer of power. By controlling that, there are a lot of grid support services that can be done by an electric vehicle charging station that we'll discuss in detail. Now, from the perspective of transmission system operators and the distribution operators, EVs can be utilized as a mobile storage to benefit the different grid operators. This is it. There is a battery capacity. For example, a vehicle like Tata Nexon EV has a battery capacity of 30 kW. So a 30 kW capacity is substantially enough for us. If number of vehicles will be very high, so the power bank, if the vehicles can act as a power bank, it will help the grid in a big way. And how it can be done, we'll discuss. The controllable nature of EV charging make them ideal for providing ancillary services. So that is another aspect, the ancillary services. That is, the ancillary services, what are they? So ancillary services are the services that is necessary to support the transmission of electric power from generators to consumers with some controllable obligations. So if you want to transfer the power from the generating station, it will be far away from the users, there will be some support that will be required for the frequency and voltage control, the stability of the system. For that, electric vehicle charging stations and electric vehicles can play a pivotal role. But the problem is, if I am having a vehicle, I'm thinking that I'm going to be an ancillary service supporter to the electric grid. Like this is the electric grid it is transferring massive volume, massive amount of power, and megawatts of power, and I'm coming up with my 30 kW. So the grid will operator can it operate it with my 30 kW alone? No, it's not possible. So the bid volume to support the ancillary services should be there. Will be a minimum bid volume should be there. So as a single entity, as a EV, it cannot participate in this market. At the time, there is another business opportunity coming, the aggregator. If I am working as an aggregator, I am bringing hundreds of vehicles together. I'm bringing my friends' vehicles. I'm bringing them. I'm controlling them together, and I'm playing as an aggregator with the grid operator. And I'm telling them, I'll provide you this much of power whenever there is a demand. So the aggregator can group the fleets, and these fleet of EVs can participate in ancillary service market to maintain the minimum bid volume, and it can thus control the grid, help controlling the grid, in fact. So this is a large elaboration of the support structure as an electric vehicle charging infrastructure, how it is helping the system. So what are the applications, things like that. So an EV charger, primary application, as I said earlier, it will be charging the EV batteries to commute, of course. Then the application of V2X will explain in detail. This is about the distribution operator or a private user, congestion management, local voltage support, behind the meter optimization, help in load leveling. These are topics that need to be explained in detail. If we that should be different presentation as well. So I'm not going into all of them. Then ancillary services. Again, ancillary services are basically the frequency regulations. We know that in a grid, whenever the demand of power is high or demand is less, the generation has to be controlled. The governor has to play a major role, governor of a generating station, that means for a generator. So what happens is the frequency should be in limits. It has to be maintained in a limit that is being accepted by the grid code or the grid operators. So if it is varying, it is not acceptable. So it should be maintained at a particular level. 50 hertz, there is a variation is been accepted. It shouldn't vary beyond that. So at that time, the frequency control is a very big thing, because suddenly huge demand of power is coming. At that time, the generators should kick in. So it should help it in controlling. As the demand is getting high, the frequency will go down. When the demand is getting low and the generation is high, the frequency will go up. In either way, the load and generation need to be balanced. At that time, the electric vehicles can play a pivotal role. And how it will be done, we can talk about in the session. It's called as smart charging. And the RE integration is a very important aspect of electric vehicle charging infrastructure is RE integration, because the renewable energy is one of the major players that is actually substantially changing the shareholding in total power generation. As we are all going green, the conventional power stations are getting closed day by day, and we are expecting to end the requirement from the conventional power stations. So for that, the RE integration with electric vehicles, how it will affect, and we'll discuss in detail about that session, how RE integration is going to be an advantageous point of view, and why we should promote that, and what are the problems that's been created by RE integration as well. Now coming to the major topic that is called a vehicle to X system, V2X. You might have heard about V2G. So why I'm writing as vehicle to X is, X can be anything. So from vehicle, we are giving power, or we are taking power. This is basically the concept of V2X system. V2X is the concept of discharging the electric vehicle battery in order to serve secondary purpose. As I said, the primary purpose of an electric vehicle charger is to charge the vehicle. What is the secondary? This power can be given to someone else, vice versa. So if we are using the concept of discharging the EV battery, there's a battery inside the vehicle that is getting charged, that is called EV charging. If that EV battery is getting discharged and giving for secondary purposes, this is the V2X system. So it can be used to manage charging, to provide the grid support services. If we are supporting the grids in many ways, it is called V2G. Similarly, if you are powering a home, as I said earlier, in our home, the total power demand will be 3 kW. That is or 4 kW is the total connected load. At peak, when the peak power requirement is high and the price of peak power, the time of the day tariff will come. If it is not there in residential loads in the future as well, when smart charging and smart metering will come, prepaid metering will come. At that time, what happens is you can use your electric vehicle. It is fully charged. It has a 30 kW capacity or minimum 20 to 40 kW and above for some other vehicles. You can use this battery and you can use the stored energy in the daytime, which we bought for a cheaper value, and it can be charged. This power can be used to light the home, that means the power the home, that is V2H. Similarly, building to a microgrid, that will come. And other purposes, off-grid situations like campsites, I have a picture of it, I'll show you that. So what are the requirements of V2X? How do we actually do the V2X technology? V2X technology needs added electrical infrastructure compared to standard charging or even smart charging. So it is not easy to actually implement the vehicle to grid technology, because in the present way we cannot simply connect our vehicle to the grid. We cannot simply communicate with them. It need an added infrastructure, and actually that is the need of the future. When in the future it will be sure that our grids will be converted to microgrids and smart grids, and that time the vehicle to grid concept will emerge more significance, and that infrastructure required for it will be developed. It needs a bidirectional converter to convert the DC power from the batteries to AC power synchronized to the grid. So we don't know if the present charging infrastructures, mean the manufacturers are coming up with equipments which have the communication capacity or the converting capacity of bidirectional conversion from the vehicle to grid. Because at present we are asking them to set up charging stations which is only for charging vehicles. We never told them this is supposed to be for V2G, whether it can be converted to that. We never give them orders to that. So the system has to shape from there itself. This conversion equipment is generally housed in the EVSE. As we know, this is basically a bidirectional converter. It can convert in either way. So the equipment should be like that. So it should be ready for that. The robust communication infrastructure is also needed to relay information back and forth between the EV and grid. So that is very important. Again, the energy management software, I think you have come across the central management system in the previous sessions. That is a very important aspect of EV charger. When this software management will be very, very, very important. And renewable energy data centers also, that we'll discuss later. So this communication between EV infrastructure and the grid, that should be solid, and that should be free from cyber attacks. That should be very strong. So that creation is going to be the biggest challenge when we are setting up EV charging infrastructure that is connected to the vehicle V2G system. Further, additional technical requirement must be met in case of V2X applications, such as appropriate loss of mains. This is nothing. This is like the anti-islanding effect when it comes to this solar PV applications, where we are connecting solar panels to the grid. We need to make sure that when this grid is has a power failure, where they are operating in for maintenance or anything, at that time the power generated from the solar panel should not go to the grid. There should be a balance of that. There should be a control of that. That mechanism should be strongly put here also. And there will be, of course, two metering. Whatever that is required, bidirectional metering should be there. Whatever required in the solar metering, net metering, similar to that will also be required for an EV charging infrastructure when it is being connected to the grid. So these are the requirements of V2X, and we can see the picture from this. The vehicle, which can be the battery of the vehicle can be discharged, and that can power the single customer here, that is at home. Not to the building. You are working in an office. You have like too many vehicles are there. You can charge them at the daytime, and whenever there is a power requirement in that place, so you can use the power from the vehicle as well. The third party's vehicle discharges to wider grid that we have discussed now. Now we are going to a campsite or at a very remote location. At that time, we want to power the camp, or there is no network, no grid, nothing is there. At that time, in an off-grid location also, you can use your vehicle battery to power the campsite or whatever locations that you require. Again, another classification you can see is V0G and V1G. That is, if the charging is managed, V2G is managed by a single customer. If I have a vehicle and I am charging to, I'm just managing myself, that is called a V0G. Even G is a system that is charging managed by system on a customer's behalf. The system is actually controlling it. There will be more advances to that in the future. This is again charging and discharging. That's what we see. Again, this is the schematic diagram of V2G. You can see the electric vehicle here. The electric vehicle is getting, it has a battery, as you can see. This electric vehicle is getting charged from the V2X unit, means the electric vehicle charger only. It can operate as both the charger and the discharger. It will charge the electric vehicle when it require, and it will supply to the home or grid or whatever, wherever. So there is a cloud platform that is very important. The communication aspect is again very important. I think you have a session on communication of EV charging infrastructure in this total program also, because the central management system, the communication between different chargers, central management system, and the creation of one single data center that manages the entire system, that is going to be not so an easy task, because number of chargers are coming. Each charging each charging station is being operated by a CPO, charge point operator, and whenever a numerous number of charge point operators are there, the problem of connecting them together will be a huge issue for a grid operator that we are also facing at present. Anyway, that we'll discuss later. Coming to the V2G services. In vehicle to grid service, how all can it be helped? The electric vehicle, how it will support the grid? These are some of the examples. It can operate as a spinning reserve. You know that spinning reserves are generators which are running in parallel and which are not connected to the load. Whenever there is a demand is there, we'll connect this load, connect the load to this particular generator, or we'll bring the generator into the grid. But we'll keep them on reserve. It will be spinning as well. Similarly, the electric vehicle electric batteries can operate as spinning reserves in V2G concept. Whenever there is a requirement of power, additional power is required from some place, at that time we can, the aggregator has this many number of vehicles, we can ask the aggregator, get them on the grid. So the aggregator will connect these vehicles to the grid, this many volume of vehicles to the grid, and the power can be provided. At the same time, there's one more thing that can also be done, reverse spinning effect. That is again negative. That means negative spinning reserve. Negative spinning reserve is something that has been, numerous number of electric vehicles are getting charged at the time. So the grid operator sees that there is actually power shortage is there. We need to some issues there where the power demand should be reduced. Instead of going for a load shedding, we can manage and control these electric vehicles which are being. When we are looking at this, the rate of power charging, look at that. 1,000 electric vehicles are charging. 1 megawatt requirement is there from all over there or more. We can control the transfer of power and we can reduce to 50. If it is connected to the grid and the grid operator has a control over it, it can manage the power transfer. It can control it. It's the controllable nature, the very controllable nature of the electric vehicle charging is going to be the real gift that is we are going to face in the future when it comes to a grid operator's point of view. This uncontrolled nature, by using a user, when it is being converted into a controlled nature using, it is going to be very helpful, and many renewable energy sources. And one more thing that we should understand is coming to the frequency regulation. The frequency issue, frequency support is a very important aspect. I was not going to the details of it. The inertial support, the kinetic energy that is stored in the rotational masses of the generators, that is being used as an inertial support. Whenever there is a sudden change in the system, it will act as an inertial support. But what happens is then, as the renewable integration is more into the grid, more number of renewable power is coming, the inertial support is reducing. This decaying year by year. With more and more renewable energy, this inertial support will come to an end. At that time, the grid collapse. The grid is more vulnerable to collapsing, since there is no inertial support to manage the system from the changes, the sudden change in load, sudden demand in load, whichever the instantaneous demands. So at that time, the electric vehicle charging infrastructures as a fleet aggregators operation, it can control it. It can control the power flow. It can control the power requirement or sudden dip in the power requirement. Whatever is, in either way it can help. Another way it is helping is the peak power shaving. This is a process of reducing the amount of energy that is purchased from the utility companies during the peak hours of energy demand. So during the peak hours, if you are going to sit in a load dispatch center of any state or uh, in power exchanges, you can see that there will be huge demand of power at that time. So whenever there is additional demand, when you're trying to purchase the power from the power exchange, what happens is the price will go high. We'll try to shave that requirement, because otherwise it will be huge problem to already troubled discoms. Distribution companies are already facing a lot of issues financially. So this demand, peak power shaving, is very much requirement for them. So that can also be helped by the electric vehicle charges, and we'll explain it how it has been done using the RE integration. Now, coming to the utilization of electric vehicles for better RE grid integration. The problem with renewable energy is that it's very nature of uh, unpredictable nature. Basically, if it come to the solar power panels, we know that it can only generate power when the sun is there, when the sun is shining. Otherwise, we will not get the power. For wind operations, we know that whenever the wind is there, its nature is also very changing. So we cannot always depend upon the RE. There will be excess generation of renewable energy. Sometimes we don't need this much of energy into the grid. This much of power comes, that means it will affect the frequency. So we need to curtail it. Sometimes whenever we need it, it will not come. So the RE renewable energy may also need to be curtailed to ensure system stability. But as curtailment of RE sources leads to non-optimal operation of grid in terms of economics. Yeah, that is the part, economics. In a daytime, this huge power generation from solar panels are there. The solar panels, many power is being getting generated. At that time, huge volume is generated, but there is no demand. If you are converting this demand to, or targeting electric vehicle, there are a lot of electric vehicles are there, they have batteries are there, a cheap power is available at daytime from renewable energy. If that can be if we are directing them to the electric vehicles can charge this renewable energy from the day where the power is coming in a cheap rate. It can be, the electric vehicles can charge them. So this power is getting at a cheaper rate, and this power can be utilized by the electric vehicle owner or the fleet aggregator, and that can be given to the grid operator at the peak time, or he can use it by himself during the high priced peak power. So with the added shortage, the periods where generation exceeds the demand, that's the point. There is a demand, so generation is more than the demand. So extra generation can just be used for charging the storage and vice versa. So this stochastic behavior of plug-in time of EVs and the SOC level impacts the ability to facilitate RE integration. So how can we use the electric vehicles for a better renewable energy grid integration? So electric vehicles with the V2G capabilities can facilitate RE integration, as they can behave similarly to the grid storage facilities. So basically the bulk storage systems are what we are thinking about in power system. When the battery technology is getting matured, the power generated can be stored in bulk to the energy store. But at present it is not viable because of the rate of the lithium ion battery is not to a level where we can be taken as a viable project. But electric vehicles are there, that battery can be used like this, and they can act as storage devices. Even in unidirectional charging also, we were talking about bidirectional because the power is being transferring to the grid. But even in case of unidirectional charging, that can also be utilized for RE integration. For unidirectional charging, the EV charging load needs to be controlled depending upon the RE integration. That's what I said. So the power is generating from the renewable energy that can be directed to electric vehicle batteries. So whenever there's excess generation, we can transfer it to there. This is how we can utilize it. During the peak RE generation periods, the electric vehicle charging load may be increased so that RE generation is used to charge the vehicle. This is the concept that I said. As a residential customer with both on-site generation and EV can improve their self-consumption on energy. This is nothing. But if you're using this, if you have a rooftop solar system, you are generating power in a day, and that much power is not required by you in daytime. So you can store it into the battery of electric vehicle, and you can use it at peak time. So the reduction of electricity cost will come also down. As as an employee from an electrical utility, I shouldn't say this, but still, as a as an individual's perspective, you don't have to give a higher rate to electricity because you can use the power that is being generated and that is being wasted for nothing. That can be stored in electric vehicles and can be taken at a later time. Utilization of use for this is what I was talking about, the rooftop part. Coming to the advantages of utilizing the renewable energy sources for EV charging. So the goal of transition of electric vehicle from IC engine vehicles is to reduce the greenhouse gas emission. So the use of renewable energy for charging the electric vehicle would further this cause. So this is an idea where green meets green. Electric vehicles are for avoiding IC engines. At the same time, green energy can be generated from renewable energy sources. The conventional pollution making thermal plants can be avoided. So what happens is green meets green. It's better for the environment as well. So the on-site RE sources can help reduce the energy drawn from the grid for EV charging thereby. Again, another part is the utilizing of renewable energy really comes to the decentralized generation. The decentralized generation can be well taken care of by the regional EV charging stations. So that's the system that will be more reliable and useful at the end by making renewable energy and electric vehicle charging integrated. This is what I said, distributed generation. So as EVs are controllable loads, so by aligning electric vehicle charging with periods of high RE integration generation, the detrimental impacts of renewable energy generation can also be minimized. So the advantage finally I conclude like this. The renewable energy sources have started replacing the conventional generating units. The requirements of ancillary services has increased in order to maintain the grid stability. So using the smart charging of electric vehicles, they can be utilized as resources to supply ancillary services from the demand side. Now coming to one more thing, that is how can you schedule the EV? So it's very simple to say this. Throughout my presentation, I was talking about it. We can control the electric vehicle. We can control it. We can charge it whenever we require. We can give power bidirectionally. We can integrate it with renewable. It's very easy to say, but how can you do it in practical? So this is where we are going to face the dilemma: the scheduling of electric vehicle with RE integration, facilitating higher usage of RE-based EV charging. Some methodologies we can be used. One is the simplest among them is variable electricity price. So to attract people, we can say that during daytime where RE generation is high, we can have a different pricing. Say if the power is being given for 6 rupees per unit, you can say that if you are using electric vehicle charging for a period where the RE generation is high, we can give it for 3 rupees or 3.5 rupees. People will be interested there will be mass volume, otherwise it is not going to be used or it will be curtailed. The economics will be better. By reducing the electricity prices during the high RE generation periods, the EV users would be incentivized to charge their EV during the period of high RE generation. Another way of using the renewable energy for EV charging is directly controlling the charging power of EVSE. That means that I have already mentioned it. Whenever there is a power requirement or sudden change in power, we can control this power requirement, power demand. We can change the transfer of power if the grid operator is been controlling with the electric vehicle through RE integration. The EV should all be allowed to utilize the full rated charging power if there is a sufficient. That's what I said. Whenever sufficient power is there from renewable energy, the electric vehicle owner can utilize it and you can charge the vehicle fully. If it is not there, only the conventional power is available, then we can either increase the power or we can reduce the amount of power that can be supplied at that time. So determine again, now coming to the important fact, how exactly it is being done. We should know how to integrate the electric vehicle to the renewable energy. So we should know what is the actual what are the renewable energy sources are available at present in the grid, when it is coming, how much power it is creating. So these things should be available. For this, we need a renewable energy data center which will give us exact data. Renewable energy data center will tell us how much power is being getting generated from each power plant, solar plant or wind plant, whichever renewable plants are associated with the grid. It will even predict you how much power it will create for next month as well. So there will be forecasting as well. In Kerala State Electricity Board, we have set up a renewable energy data center in Trivandrum that is functional with a few renewable energy sources are connected to it. We are in the first phase only. We are expanding it. After some time, what we'll do is we'll make it as a renewable energy integration with EV also in this, because the renewable energy data center will provide the information on all the renewable supply. Then we'll come with electric vehicle data center. So that means EV charging infrastructure, EV data center will provide the total control over all the vehicles in Kerala with the help of the aggregators. So we will combine them together and we'll do the operations. It is nowhere now. It's only in the phase 1. Vehicles should come more into the market, the aggregators should come, EV chargers should come. So there is a lot of work in there. Again, we need a lot of support and help from the researchers to actually coming to a proper solution of how to execute it. The final solution of active scheduling of EV charging is by the grid operator, considering the system state. Again, one more thing I missed is the RE integration of EV charging is already been commercially deployed in Denmark. It is considered as one of the highest share of energy production from RE sources. You can see a lot of offshore wind farms are there in Denmark, where many the renewable power generation is more than 40%, I think. So with that, they are managing with the EV also in a commercial basis. So hopefully we will also reach there at some point. I'll conclude the presentation by explaining the concept of smart charging. Before smart charging, we should know what is dumb charging. Dumb charging is nothing. It is we are charging from our plug. Refueling electric vehicle via charging the battery using conventional charging practices with household facility system. That's dumb charging. Like how we are charging a laptop or mobile phone, we are charging it from plug and play from our home. This is what is called dumb charging. What happens with this is an uncontrolled type of charging that facilitate the plug and play mechanism. But the problem is, with the significant EV integration using dumb charging, it will negatively impact the grid. As I said, the demand will be high. Everyone is directly charging from their home. The demand across the state, across the country will go skyrocketing. So this leads to a lot of issues that we were mentioning earlier. That is the point where the EV charging is coinciding with the peak power. So in order to mitigate these issues, we have a solution that is called a smart charging. The smart charging will take care of all the issues. So how it is taking care is the smart charging, as I said earlier, the renewable energy scheduling, the maximum utilization of renewable energy, supporting the EV, getting help from EV for the ancillary services, making EV as a backup storage, making EV as a spinning reserve. So this how everything is being done using smart charging. So smart charging actually has two stakeholders. One is of course the EV owner, and the second one is the system operator. The thing is, the system operator has his requirements and EV owner has his objectives. For a system operator, when you look into it, what he needs is overall system cost minimization. He can use the renewable energy, excess renewable energy power that can be transferred to the electric vehicle, so that excess renewable is being cached, so that system is taken care of. Again, maximization of RE utilization, these 2 points. Again, load leveling, spinning reserves, frequency control, everything that can be done, grid stability maintain. These are the reason why a system operator is approaching smart charging. System operator can manage all the controllable nature of charging, and he can achieve everything. At the same time, what is the perspective of an EV owner? He has nothing but, if I am an EV owner, what I need is I need to get power from the grid or anywhere, so that my vehicle will be charged at a cheaper cost. So the grid operator is saying, I'll provide you power during the daytime at a lesser cost at this particular time. I'm ready. So satisfaction is there. From my side, I am not, I'm like 5 rupees per unit, 4 rupees per unit, 3 rupees per unit. I'm getting a different rates at this particular time. At a for 30 units is for fully charging for a normal premium vehicle. So 30 into 5, 150 rupees I am paying them, and I can go up to 200, 250 kilometers. It can also be reduced. So there is a satisfaction level is also there, and the grid stability maintaining. I'm also being a partner that is helping to maintain the grid. So these are the aspects that I wanted to discuss. This is again a very technical and elaborative topic. I don't know how much I could convey. I'm not a very expert in this area also, but these are the challenges that we were facing when we are thinking about setting up of more electric vehicle charging infrastructures in Kerala, in the state, and the issues that we were primarily feeling this could happen. And even though these are the basic idea is to control the electric vehicle charging, but again, to make it happen in a reliable, I mean in a practical way, we need a lot of case studies and we need a lot of applications, the control of the software, the management. Again, the grid is again vulnerable to attacks. If we are connecting so much vehicles to it, through softwares, if these softwares are vulnerable to cyber attacks, issues are there, it will affect the grid as well. So a lot of things to be taken care of. So I hope that in my presentation, what I wanted to discuss was what are the impacts that are actually happening in the electrical grid due to the integration of electric vehicles. Now, what are the opportunities the electric vehicles that is providing to the grid by the EV integration? And what is the concept of V2G, V2X systems, and finally, the renewable integration and the smart charging. With this, I hope that there will be a future where so many electric vehicles will come to our market, and it will really control the whole power system also. And some of you, or most all of you, will come up with good solutions and work as in different aspects of electric vehicle charging and its grid integration, and make our country a stronger one in EV charging adoption. Thank you so much for giving me this opportunity. Thank you.
Thank you, Sajin, for an incredible knowledge transfer session. Now I request the participants to ask queries.
Good morning, sir.
Morning.
Yeah, actually, it is like a grid interactive means for electric vehicle. The main problem lies in battery, and
Okay.
the battery life cycle cost much. So in that case, if you are going with the grid interactive means, then the battery life cycle will get reduced by half, which will increase the cost of the maintenance of EV, right?
Yeah, of course. That is again the studies there. People are working on that. I think this continuous charging and discharging will again, as you said, it will affect the life of the battery. So that issue also should be taken care of. So the battery life cycle should be able to manage this. What you said is a relevant point, sir.
And what is my observation is in the electric vehicle, actually PV is almost saturated. Electronics is almost saturated. The thing is, chemical engineer supposed to work hard, I think.
Exactly. The material part is the important thing. Again, what I can understand is the C rate of the vehicles. When you have a high C rate vehicle, it has high power density. So that is why we cannot have high range vehicles at present. What I understand from the EV manufacturer side. So these area people should work on, as you suggest, sir. It will be very helpful in for every one of us.
Thank you, sir. Nice presentation. Thank you.
Thank you.
Any other queries from participant side?
Hello, sir. Can you hear me, sir?
Yeah, sure. Tell me.
Sir, I am Dr. Charles. So I have one doubt regarding that because one of my friend is want to buy the electrical vehicle. That time we are getting some information from the showroom that cost is very high, sir, depending upon the battery. So what you are already told us, the battery, how the power is going to be consumption, how that rate is going to be the unit wise, the rate and all those things. Compared to the petrol vehicle, somewhat this particular electrical vehicle is getting some rate high. Whether it is possible to reduce the amount for using this particular electric vehicle, sir?
Okay.
Whether it is possible?
Okay. I think your question is the rate of
Yes,
price
yes.
of electric vehicle is high,
Yes,
and
sir.
whether it is compared to an a conventional IC
Yes,
engine,
sir.
will it be viable?
Suppose we are doing the electrical charges, it may be high. Suppose we are converted to the renewable energy, that time he may be chance to reduce the amount. That's my question.
Actually, that was my presentation again. That is
Okay.
actually based on the grid operator. If you have a simple solution to that is, if you have a solar plant inside your home,
Yes.
okay, you can power
Okay,
it from
okay.
there itself. That
Okay,
itself
okay.
will lie the solution. Again,
Okay.
even if you are going for a DC fast charger,
Okay.
that means public charging station, it will cost up to 15 rupees or above per unit for
Yes.
fast charging.
Okay.
At home,
Yes.
you have to pay only whatever charge you are at present paying for unit. Okay. Uh,
Yes.
so in that is actually you can do it every day. Only during transportation, only from
Yes.
long distance, you need to use the fast
Yes.
charging stations.
So before
Again,
that we should know.
again
Okay.
that price is also substantially less. I can explain that at
Oh,
present this Tata Nexon, it has a 30 kW is the total capacity. If you are
okay.
charging with 415 rupees maximum rate,
Okay.
15 into 30, that means 450 rupees you are charging from public charging
Okay.
station. You
Okay.
can go up to 250 kilometers range, so you can
Okay.
understand what is the rate per unit for per kilometer. Maximum 2
Okay.
rupees, 1.5 to
Okay.
2 rupees it will be there. If you are charging from your home, it will maximum go to 5 to 6 rupees or 7 rupees. Say 7 rupees. 7 into
Okay.
3, 210 rupees. You are charging
Okay.
totally from the grid. Again, what is the cost? Maximum 1 rupee.
Okay.
1 to 1.2 rupees. That's it. So
Yes.
anyway, this is economical. The only problem that you face is the initial high cost. Again, I think
Yes,
the
sir. Yes,
government
sir.
is
That is the main thing, sir. Yes,
yeah,
sir.
I understand. The government is
Ah.
intervening at many places to reduce and offering many incentives, and it will increase also. I think in some states per KW they are offering incentives, and there is a income tax benefit also for
Yes, sir.
the interest part of the electric vehicle purchase. So if you are
Yes.
purchasing for 17 lakhs, the interest rate there you can reduce in the IT also. So that way also you can come down the amount.
Yes, yes. On the whole, whether we are using that particular vehicle, the government is also giving some allowances,
Yeah,
like
yeah.
that way. Okay, so that is the better thing. So before that, from your explanation, I came to know that before that we should identify and understand how much we are going to travel. That is a very important thing. Like that way, we have to do the charging in things.
Yeah, exactly.
Okay.
Okay.
Yes, sir. I will understand, sir, what your concept. Thanks, sir. Nice to talk with you, sir.
Thank you.
Thank you, sir. Thank you.
Good morning, sir.
Morning.
Myself, Professor Sheikh from Ahmednagar, Maharashtra.
Tell me, Mr. Sheikh.
Sir, my question is, which type of material is used in a electrical vehicle battery?
It's lithium-ion battery.
Lithium-ion battery.
I think you have
And
a session coming on the battery, right? Next one.
yeah. Okay, sir. So, one more question, sir. What are the present difficulties to prepare charging stations at various locations?
Actually, I have a session coming in the afternoon that I'll talk about how to set up and what are the issues, everything associated with that whole session. Okay.
Okay, sir. Okay. Thank you.
Okay.
Any other queries from participant side? I request any of the two participants to say out of thanks to Sajin. Varalakshmi, ma'am. Varalakshmi, ma'am, can you please give feedback to Sajin? Some net connection issue.
Hello.
Mohammed Asim, sir. Yes, ma'am.
Uh,
Please give
Yes,
your
sir.
feedback.
good evening. Good morning, sir. Hello. Am I audible?
Yes, you are audible. You are audible.
Yeah, you're audible.
Actually, let me thank Professor Renu for arranging this nice session for all of us, and many thanks to Engineer Sajin, who has given all insight about EV and many information that is helpful for us. And let me thanks the college COET also for arranging this nice Atal FDP for all of us. Thank you everybody.
Thank you, ma'am. Thank you, Sajin, for an incredible knowledge transfer session. Even though EV revolutions are welcomed globally, addressing the grid issues created by them is also inevitable. I remember about the quote for which we used write essays during our school time. That is actually for every boon there is a curse. I think in our scenario also the boon part are the benefits gained with the electric vehicle revolution, whereas the curse part are the troubles caused by them over the grid. Actually, you gave us an insight towards the troubles caused by EV penetration in the grid. The enormous opportunities founding research in this field. Even though EV revolution are welcomed globally, addressing the grid issues created by them are also inevitable. We all are looking forward to hear from you much more in detail about development of EV charging infrastructure and multi-stakeholder governance of EV charging in the third session of the day. Thank you, Sajid.
Okay, sir.
Thank you. Thank you, Renu.
कंपेयर टू कैसे करते हो दो ग्राम कंपेयर करके हम क्या करते हैं दिस वी गोइंग टू फाइंड आउट कंपैरेटिव मेथड दिस कंपैरिजन टू मेथड्स graphical comparative method or non-graphical comparison.
We will revert for the third session, sorry, for the second session at 11:50. Some people are saying that there are some issues with the attendance link. No issues, I will rectify it and I will upload it in the WhatsApp group. Like our technical team will look into it. I have to arrange a meeting link and all with the second speaker. So, no, don't worry. I will be sharing you the attendance in this in the WhatsApp group.
Don't compare. We are going to do the zones.
Yes, Praveen, sir, I am sharing the attendance link in the WhatsApp group. Yes, our technical team has said that the attendance link is working properly. All of you are requested to check the link once again. I will be sharing the link once again here.